Welcome everybody. My name is Rasmus Bro from University of Copenhagen in Denmark. And today we have Anastasia Aidini, who I thought were from University. You used to be from University of Crete, maybe.
Yes.
Okay, but now you're in the Foundation for Research and Technology, RES or something. And she's going to talk about a new method she has developed called few-shot classification using tensor completion. So please, Anastasia.
Yes. Hello, everyone. Thank you for the invitation. Generally, I'm working on the acquisition and analysis of high-dimensional observations using tensor analysis combined with machine learning techniques. And today I will present a new tensor learning approach for the supervised classification problem. This work was co-authored by Dr. Zakatakis and Professor Sidiropoulos and Tsakalidis, and it was presented at the Silomar conference a few months ago. I will start presenting the problem and the challenges that we addressed in this work. Next, I will present the basic idea and the algorithm of the proposed method, and then I will conclude this presentation with some results on real-world classification tasks. Analysis of observations by means of supervised classification is crucial in many real-world applications, such as the filtering of spam emails, image categorization, and medical diagnosis for several diseases. The goal of classification is the prediction of a discrete variable, which denotes the class label associated with observations. Many machine learning techniques have been introduced to solve this problem, including kernel methods, random forest, and neural networks. However, the existing machine learning approaches work well depending on the problem and the data characteristics, and it is unknown in advance which method will perform best for any problem. And they often require a large amount of training samples. Recently, tensor decomposition techniques have been increasingly utilized in machine learning, and specifically for the classification problem, tensor models have been used for feature extraction, and then a separate classifier is applied to perform the classification task given the extracted features. In contrast, in this work, we propose a new classifier by formulating the classification problem as a tensor completion problem. Specifically, given a number of training samples X and their corresponding labels Y, we consider that the label of each sample is the output of a nonlinear function of the input X that can be modeled as a higher order tensor that consists of the labels of all samples. The tuple of the input variables in this formulation indicates the indices in this tensor, and the cell contents will be the corresponding label. The number of dimensions of this label tensor will be the input size n, and the size of each dimension will be the range of input values in the corresponding dimension. Then, given a new data point, the corresponding tensor cell is queried, and its context is used as a predictor. However, only a small fraction of the tensor entries can be obtained from the training samples. Therefore, we have to complete this label tensor in order to predict the labels of new samples. The idea to model a general nonlinear function as a higher-order tensor with missing entries, was first introduced by Kargas and Sidiropoulos for the regression problem. However, in the classification problem, the labeled tensor has discrete integer values, and the existing tensor completion methods are designed for real-valued entries. To address this, we propose a new tensor learning model combining classification loss function with tensor decomposition techniques. And specifically, we measure the performance of our classification model using the hinge loss function, which is defined by the sum for every class C, except for the true class Ys of each sample S, of the maximum values between 0 and the quantity of the predicted scores of our model corresponding to the class C, minus the predicted scores corresponding to the true class Ys, plus delta, a parameter that indicates the desired margin between our classes. Therefore, we want the score of the true class to be greater than the sum of the scores of the other classes by a margin delta. In our case, we encode the scores in a tensor with an additional dimension of size the number of different classes for the scores of each class. Therefore, for each entry of the labeled tensor, each entry of the labeled tensor corresponds to a vector in the score tensor for the scores of each class of this sample. However, only a small fraction of the score tensor entries can be easily obtained from a number of training samples. Therefore, we have to complete the score tensor to recover the scores of the unlabeled samples. And to complete the score tensor, we impose a low rank constraint on it to extract the correlations in the training data using Tucker decomposition with orthogonal factor matrices. Specifically, the Tucker decomposition decomposes a tensor into a number and into a factor matrix for each dimension. The factor matrix is D1 to Dn plus 1 in our case, and the core tensor G of coefficients with smaller dimensions than the original tensor. And specifically, the dimensions of the core tensor actually indicate the rank of each dimension of the tensor that we call a multilinear rank of the tensor. Therefore, we minimize the hinge loss function of the score tensor A and its Tucker decomposition with orthogonal factor matrices on the available training samples, where the parameter lambda acts as a balancing weight between the terms of our optimization problem. And to solve this problem, we applied alternating optimization. Specifically, we optimize each individual variable iteratively until convergence or a maximum number of iterations, while keeping the other variables fixed. And specifically for the score tensor update, we used gradient descent following this update rule at each inner iteration, where gamma is the step size parameter and the partial derivative of the objective function f with respect to the score tensor A is given by these equations, taking into consideration the true class yi of each sample I. And for the factor matrices and the core tensor update, we used least squares. Following these update rules at its outer iteration. And specifically for the factor matrices, we also applied the QR factorization after their update in order to impose the orthogonality constraint on them. Therefore, we propose in this work a tensor learning model that captures the interactions between the predictors and recovers the unobserved labels by combining a classification function with tensor decomposition techniques. And specifically, we learn the score tensor in the training process, and then to predict the label of a new sample, we take the score. We take the scores that correspond to the last dimension of the length score tensor in the position indicated by the sample values, and we classify it to the class with the highest score. And to evaluate the proposed method, we performed experiments on several real-world classification tasks using datasets obtained from the UCI machine learning repository. And specifically for its experiment, we used 80% of the dataset for training and the remaining for testing. And we used a small part of the training set to perform cross-validation for parameter tuning on 10 Monte Carlo simulations. Firstly, we investigated in this figure the empirical convergence of the proposed method for different step sizes of the gradient step of the score tensor update. And as we observe, the convergence is monotone using a small step size, while there are small spikes in the loss using when the step size is large enough. Therefore, we selected the step size equal to 0.01 in our experiments in order to have a great performance with monotone convergence. We also examined the multilinear rank of the score tensor, which is an important parameter of the proposed method for different sizes of the training set. As it was expected, the testing accuracy increases as the size of the training set increasing, since more data are available and fewer entries in the score tensor are missing. We also observed that the performance of the proposed method is better using multilinear rank 2 in its case, indicating the true multilinear rank of the score tensor. Note here that for this dataset, the size of each dimension of the score tensor is 5. This is why the rank takes values from 1 to 5. And we always take the full rank for the dimension that corresponds to the classes, the last dimension. And finally, we compared our algorithm with other classification methods on different datasets. And specifically, we used random forest, support vector machine, and multi-layer perceptrons with 3 hidden layers, performing cross-validation for parameter tuning on 10 Monte Carlo simulations for all methods. And the mean testing accuracies of all methods and the corresponding standard deviation values that are reported in this table indicate the efficiency of the proposed method. The small standard deviation values also indicate the consistency of the results on the randomness of the simulations. It is also verified that it is unknown in advance which of the other classification methods will perform best for any problem. As a conclusion, we proposed a classification method using tensor completion, in which a tensor of scores of all classes and possible samples is completed using a number of labeled training samples. And this new learning method combines tensor decomposition and machine learning techniques, exploiting the benefits of both fields simultaneously. It is an elegant and general method that can be efficiently applied for any problem. And as it is, and the effectiveness of the proposed method, it is verified on real-world classification tasks with a limited number of samples. Thank you.
Thank you so much. I think I have a few questions here. If anyone else has a question, please feel free to speak up or put it in the chat. But I like this very much. When you say limited data set, how small can you go? Do you have any sort of experience on that? What is the size of these data sets?
All these data sets have less than 100 training samples. Yes, except one is something, it's about 100.
Right.
Yes.
And what's the number of variables? I guess the number of variables defines the order of the tensor.
Yes, the number of variables is different for each data set. For example, for the first data set, we have four attributes, and we have 3 classes. And for the others, we have, for example, 4 or 6 or 9 attributes.
Okay. In the world I'm in, which is chemistry, we often have hundreds or thousands of variables, but the actual rank is much smaller. So we can often, do an SVD or something and have rank 10 or 15 or something. But I guess you also have to discretize the data, right? If you have continuous data, you would have to discretize it.
In this case, the data are discrete, but we can also apply the proposed method on continuous variables using a suitable basis, for example, using Fourier series.
Yeah, okay, makes sense.
Or we can discretize the data.
Right, yeah. Okay. Did you have the software available for people to try? I know I have it, but I don't know if it's publicly available.
It's not, I think it's not publicly available, but we can publish the...
Okay, so people can contact you if they're interested?
What? What did you say?
People can contact you if they are interested in the software?
Yes, of course.
That's nice. One more question. Maybe I lost something. Does it matter how you label the classes, or is it immaterial how you label the classes? Does it change anything if you say 1, 2, 3, or you say 1,200 and?
No, there's no difference.
It doesn't matter because each support tensor is independent?
Yes, the number of classes is actually the last, this last dimension.
Yeah, exactly.
Yes, so as many classes as we have, this is the size of this dimension.
Okay, I get it. Interesting. Okay, let me ask people, do we have any questions from the audience? If we don't, I can tell you that we will put the video here that we're recording on our YouTube channel, so you will be able to find it later on, and I'll put the details of Anastasia so you can contact her in case you want.
I have a question, if it's okay.
More than okay.
Okay, thank you for your talk. I really enjoyed it, and I was curious about if you could maybe re-explain the part of the loss function where you have the Lagrange equation, because for me it wasn't very clear. It was a bit too fast. So maybe if you could elaborate a bit there, like how do you get that loss function? This one and the other one as well.
And this one?
Yeah. Yes.
So this is here is the Hinge loss function, which is a classification loss function to measure the classification performance. And here is the Tucker decomposition of the score tensor A. And here, I don't know if you know the notation. It's the mode n plus 1 mode, yes, matricization of the score tensor A, which is, we unfold the tensor into a matrix with dimensions, in this case, with dimensions C, the number of classes, times the product of the input size. And we write it in this way because in order to take the scores for each sample, we have this number I1 times IN, number of samples, this number of samples, and for each sample I, we take the score, and J indicates the classes, the score for each class. And do you know the Hinge loss function?
Yeah, I heard about it for the classification.
Okay.
And then I like in the intuition of, then you have that Lagrange equation, I guess, where it's the initial problem where you want to hinge loss, and then you have somewhere the Tucker decomposition. But I couldn't make the link between, yeah, like how then you get this this loss function, because if you could, I don't know if you get my question.
How we solve this problem?
Yeah, like, you know, the Lagrange equation, like, for example, it's usually when you have subject to orthogonality and then you want to, yeah, like put that orthogonality.
The low rank constraint here, we impose the low rank constraint as a penalty.
Okay, so it's for the low rank.
We have only the orthogonality constraint in this way, in order to make simpler the problem.
And the orthogonality constraint, then you use it with the QN decomposition, so you don't have to put it in the Lagrange equation. This is what you mean.
Yes.
Okay.
Yes, we impose it later.
Sure. Okay, and also I saw in the you know, at some point you showed simulation result where you have the ranks. I'm not sure if I understood. So does it mean that they all have the same rank, like the same Tucker rank?
In this data set, the dimension, the size of its dimension is 5 of the label tensor, and we take, yes, the same rank for its dimension in this case. But we can take different rank for its dimension if we want. It's not necessary to be the same. For example, if we have if the size of its dimension differs from one dimension to another, we can take a different rank.
And how would you be able to decide which rank you choose for every dimension?
Yes, in order to decide which rank is better, we perform cross validation.
Okay.
We consider the rank as a parameter, and and according to the results on the validation set, we choose the best value for the rank.
Okay, so you wouldn't put it like in your optimization problem as another penalty?
No. We perform cross validation for parameter tuning.
Okay. All right. Yeah, that was it for me. Thank you.
Right.
Any other questions?
Hello, I don't know if I can make a comment.
Of course.
Hi, hello. My name is Gregory Tsagatakis. I'm a co-supervisor and working with Anastasia. So I just wanted to, to mention the fact that Anastasia, this is one work that Anastasia did, but there is also another interesting aspect that I think you could be interested in introducing machine learning in tensor decomposition. So this, Anastasia, I don't know if you want to say some things about the tensor decomposition learning framework, where the idea is you have training data in a machine learning framework, and you try to learn part of the decomposition similar to this work by formulating the problem through an augmented Lagrangian minimizer and appropriately minimizing the functions, right? Which I think would be of interest to you as well. So Anastasia, you want to say some things about this work?
Yes, this is another work, the tensor decomposition learning method. In this method, we are trying to introduce tensor decomposition in the machine learning frameworks, and specifically using a number of training samples, we learn a basis for each dimension, the factor matrices, and then we can take its sample, a new sample, and we can express this sample as a multilinear combination of these learned bases. And we have applied this method for comparison of high-dimensional signals.
Interesting. Did you write? Do you have a paper on this as well? Or?
Yes. It's a paper entitled Tensor Decomposition Learning for High-Dimensional Signals, I think.
Very nice. Very interesting. Okay, I like.
And of course, we can apply this method and for other problems, except for comparison.